Okay, hi everyone. So welcome to the BTPC Idea Series. Today we have a talk from Rachel Houtz, who is a postdoc at Durham University in England. She did her PhD in the States at UC Davis, and she's going to talk today about some of her work on modeling dark matter and finding the origins of the universe. So we're all very excited. Take it away.
All right, hi everyone. I'm very pleased to be here with you virtually today. Today I'm going to talk about light dark matter through resonance scanning. This is work I did in collaboration with Juna Kroon and Graham White from Triumph, and Hitoshi Murayama from UC Berkeley, and Gilly Allor from University of Washington. This is kind of the slide that I'm sure many people have seen in various versions many times before. But we have like very significant evidence that there's a new particle beyond the standard model that makes up dark matter, and that makes up like a significant portion of the mass of the universe. And we've seen this through rotation curves of galaxies and like observations of gravitational lensing versus like direct observations of photons, and then also like measurements of the cosmic microwave background. And so like it's pretty well established that there's something out there that we don't know the particle identity of. And so the question is, how is this dark matter produced? And like the most popular theory is a weakly interacting massive particle. And I'm kind of going to go like do a really quick review of how this works because it's like relevant for the production mechanism I'm going to talk about. The idea with weakly interacting massive particle dark matter is that the dark matter is in equilibrium with the standard model, and like this annihilations with the standard model like proceeds as the universe expands, and eventually like the dark matter exits thermal equilibrium as more and more of it annihilates. And when the annihilation rate falls below Hubble, the dark matter's relative abundance is set, and the yield is you can tell the yield of the dark matter that you see today. This is the most popular idea for dark matter. It's kind of like a nice explanation for why there's so much of it, just based on like what its interaction strength was and when it exited equilibrium. And there's been like an extensive search program for WIMP dark matter. And like, you know, people often say like this story is becoming more constrained. So like, if that's the case, that the story is becoming more constrained, the question is like, what is the new direction to search for dark matter? And one new direction is to look into lighter dark matter, right? So maybe like the dark matter isn't so massive, but the problem is that if you just consider like the production mechanism of like thermal production of the WIMP dark matter, usually when you go to really light masses, you run into problems because you need like higher cross sections, and this like gives you problems with like cosmological observables, for example. So you need like a production mechanism that can produce the dark matter with like weaker couplings. And so again, like a very, very popular mechanism is freeze-in dark matter. And this is basically an alternate mechanism for producing dark matter that works really well for light dark matter masses. And the idea is that the dark matter and the standard model interact, but very weakly. So I still sort of the same diagram, but I've kind of put it in reverse. And the idea is like the standard model like is in the thermal bath, but not with the dark matter. The dark matter is being produced out of equilibrium, but it still interacts with the standard model very weakly, and it is still being produced. And you can see like in this plot that I stole from Hall and friends in their first like paper where they introduced this, that like the yield of the dark matter slowly increases as more and more of it's produced until eventually like kinematically this process becomes forbidden. And then like these interactions sort of turn off and the relative abundance is set. And this is usually controlled by like the late time behavior. And this is also relevant like for the production mechanism that I'm gonna introduce. So it's kind of nice to sort of review like the two different sort of main ways people talk about producing dark matter.
Rachel, if I could ask a really quick question.
Yeah.
So I'm not super familiar with this field, so could you just explain what the x-axis is? I've seen it a few times, the m over t.
It's just the mass of the dark matter over temperature.
Okay, so this is like as a function of time because the temperature is cooling down. Okay.
Exactly. So like you know, this is kind of the way it's written is sort of like a general parameter space. But say you just have a model of dark matter that has some mass, then this is just time evolution. right? So like as the temperature decreases, time is moving forward. So like time goes, can you see? I can't even see my mouse, so I don't think you guys can. But time goes from left to right on this plot. Okay. Okay. Yeah, so those are like, okay, so I'm glad I reviewed it then. So those are the two main ideas, right? So either it starts in equilibrium, and actually they're both on this plot. So like the WIMPs are the solid lines on this plot, and then the freeze in dark matter is the dotted lines. And so yeah, the WIMPs like start in thermal equilibrium, and eventually like as the universe expands, it's like less likely for the dark matter to find friends to annihilate with, and then like it's just like exits thermal equilibrium, and it has the yield that it had at that point when it exited. And then freeze in is the idea that it's not in equilibrium, but it's very like feebly produced, and over time like it kind of builds up a population, and then it gives the relic abundance that we observe today. And so those are kind of like the two main ideas, and this works really well for light dark matter. And then like there's a lot of searches for light dark matter, like, and you can see that these searches don't really probe the same, well, you can see these searches don't really probe the same coupling. So they probe like, they can't quite get to like the same like weak couplings as the WIMP. Like they haven't like ruled out as deeply in that parameter space, but they're turning on, and they might like be able to probe freeze in scenarios soon. So this is like an interesting new direction. Like there's a lot of new searches for light dark matter. And so like when I first showed this plot of WIMP dark matter, I said like the WIMP scenario is constrained, and you see it's a lot. But like to say like what does that mean for the WIMP scenario to be constrained? Like you should probably put together like a specific model, and then when you have a specific model, then you can like really concretely answer the question like how constrained is this model? And a really good example is the Higgs portal. So like the Higgs portal weakly interacting massive particle is like a very, very simple way to couple like a singlet dark matter particle, like singlet under the standard model gauge groups, to the standard model through this Higgs portal coupling. And basically, you can see this plot here that sort of shows the parameter space of the Higgs portal dark matter. So on the x-axis, we have the mass of the WIMP, and on the y-axis, we have the portal coupling. It's like the interaction strength between the WIMP and the standard model, like through the Higgs portal. And this black line on the plot that you can see that sort of starts on the top right corner and then like has this dip that falls down and then like falls back up. This is the relic abundance curve. So this is the like combination of couplings and masses that reproduce the right relic abundance of dark matter. And you can see that like direct detection searches that are like looking for particle dark matter have ruled out a ton of this parameter space. And so this is what we mean when we say like the WIMP is very constrained, right? In this model, you can see it really clearly. And in fact, you would think like, okay, the Higgs portal is completely ruled out, except for one very specific point, which is right on the resonance, right? And so like when the dark matter is like approximately or like right on resonance, so it's like about half the Higgs mass. In that case, like this annihilation, this S-channel annihilation to the standard model is resonantly enhanced. And so you can get the same relic abundance with much, much smaller portal couplings than if you didn't have this resonant enhancement, right? Because the kinematic enhancement means for small couplings, you're getting a very large cross-section, right? For specifically the process that sets the relic abundance, but not for other processes. And that's why like direct detection hasn't ruled this out. And so this is an example of like a WIMP scenario that's very highly constrained, right? It's like only open in this one specific region. And so, yeah, I think this is like, and you know, you could choose any dark matter model you want. This one is relevant for what I'm going to talk about today, but this is what we mean when we say like the WIMP is more and more constrained. Maybe we should start looking in new directions. And then like, just to like really show you this like in another way is that if you just plot the cross section of the dark matter annihilation to the standard model as a function of the mass of the dark matter particle, you basically see this resonance peak exactly, and you kind of see something that looks like an inverse of this relic abundance curve, right? Which kind of makes sense because like this is the relic abundance curve is telling you something about the cross section and the coupling, and so if I just tell you the cross section is a function of mass, you see that like this resonance peak in the relic abundance curve looks like a dip. And yeah, for different couplings, you can see like different size cross sections, and like some areas like have like the promise to reproduce the relic abundance only right on the resonance. And so the question we asked when we started writing this paper is there some way to like increase the parameter space that benefits from resonance enhancement? And we're going to use the Higgs portal since it's a simple model to like examine this question. So can we reopen the Higgs portal? And so what we were looking for is like a Relic abundance curve that like instead of looking like this black line, instead looks more like the green sketch that I've drawn. And so what we were aiming for is light dark matter that we observe today. So like light dark matter that we see in direct detection experiments, but that remembers a history of resonant enhancement. And so that means we want dark matter that has a temperature dependent mass. And so this is like the motivation for what we wrote. And then the hope is that if now the x-axis is the dark matter we measure today, we can see like this opening up of the resonance of like the Higgs portal on the resonance peak, because the resonance behavior like affects the dark matter that is lighter today than it was in its history when it was being when its Relic abundance was set. And so like when I say a temperature dependent mass, what I mean is like dark matter that interacts with a scalar field or pseudoscalar field that undergoes a phase transition. And so like, for example, if a scalar field develops a VEV and that scalar field interacts with dark matter, and then as the field like goes from its from its high temperature VEV to its 0 temperature VEV, the dark matter mass can change from like the symmetry preserving minima gives one dark matter mass, and then the symmetry breaking minima gives another one, for example. And we're not the only people that have studied temperature dependent dark matter. Like there's a lot of citations here. It's been pretty well studied, and it's like seems to be kind of ramping up in popularity now. And you can use this for a lot of fun things, like you can kinematically open and close decay channels in the dark matter's history, or you can use the phase transition to like trigger exiting thermal equilibrium, things like this. But in general, like using dark matter that has a temperature dependent mass impacts the dark matter's Relic abundance. And what we're going to talk today about is a specific type of phase transition, where instead of like, you know, the very common one that we're used to like with electroweak symmetry breaking is that like at high temperatures, the VEV is 0, and then at low temperatures, the VEV is larger than 0. And so like things that couple to the Higgs gain mass as the Higgs settles in its minimum. We're going to talk about something that goes the other way. And that's like, you can set that up. It just depends on the shape of the potential. And so we're interested in potentials where actually the mass decreases as the temperature decreases. So like the high temperature minima corresponds to a larger value of the VEV than the low temperature minimum. And we're also not the first people that studied this. There's like this VEV flip-flop paper. So this has been done for dark matter as well. But yeah, this is the case that's interesting to us, is that the dark matter mass is decreasing with decreasing temperatures. So it's decreasing as the universe evolves forward in time. And so now I can sort of introduce the central idea of the paper. And so our idea is, all right, we have Higgs portal dark matter, but the dark matter mass is decreasing with temperature. And I showed this plot, and I'll explain like the rest of the plot. But for now, what I'm interested in showing you on this plot is the red line, which is the dark matter's mass temperature evolution. And then the dotted red line shows like when the dark matter is exactly half the Higgs mass. And then it's scaled so that it fits on the plot with the other things. So, but like qualitatively, you can see what's happening is that as the temperature decreases, the dark matter mass decreases, and eventually it passes through being half the Higgs mass, and then continues to decrease until the phase transition ends, and then it obtains its final mass today. And corresponding to that, I've also plotted the thermally average cross-section, or I guess the annihilation rate is what I've plotted specifically, and is what we've plotted specifically. This is a figure from the paper. So, and you can see that like correspondingly, right when the dark matter mass goes through half the Higgs mass, there's this huge kinematic enhancement of the cross-section due to the resonance. And so the idea is that given this like setup, we have dark matter mass that generically scans through the resonance at some point in its history, right? And you can like vary the different parameters and get different final masses for the dark matter, but all of it remembers this history of resonant enhancement. And then dark matter obtains its final light mass after losing contact with the thermal bath. So the idea is that it like, it either was never in equilibrium or it exited equilibrium after the resonance. And then the phase transition continues and then ends. And then it obtains its light mass after it's no longer in thermal contact. with everything else. So like to speak again specifically about this model is like we're going to talk about a Dirac fermion dark matter, singlet under the standard model gauge groups. And then we're going to give it the standard WIMP-like Higgs portal interactions at first. So it's just like fermion dark matter that couples to the Higgs through the Higgs portal. And note the way we've written this, our Higgs portal coupling breaks SU2L. And so like our coupling that we've chosen is proportional to the VEV over some like new physics scale lambda. You could write this a different way so that the coupling is dimensionful, but this is like nice to have like a dimensionless coupling, and just remember that even though this coupling is dimensionless, you can always make it very small by increasing the EFT scale, right? So there's no like tuning for a very, very small coupling of the Higgs portal. And like, you know, you could just as easily rewrite this as some different lambda times V times H times chi bar chi, and then you get a dimensionful coupling, and then it would be natural to assume that the coupling could be very, very small by raising the EFT scale. And so then we're going to specify, so like first, we're going to talk about the next step, which is morphing the dark matter mass. So in our setup, the dark matter fermion couples to a light pseudoscalar field called the morphon, and it couples via this interaction. And then for now, I've just given like a sketch of the potential for the morphon, but when I specify a concrete model, I can show you something more concrete. But the idea is that the morphon obtains a temperature-dependent VEV. And so in this way, our morphon field morphs the dark matter mass as the VEV of the morphon changes. And you can see this, how this Yukawa coupling, once the morphon obtains a VEV, like turns into something that modifies the mass of the dark matter. And then specifically, like I said before, we're interested in VEVs that are larger at higher temperatures and smaller at T = 0 temperature. And so to be more specific, I can tell you like the model that we used. And so the model we used that like we thought had really nice behavior, specifically what we're looking for is something that like scans. So we wanted the mass to sort of like scan through many values before the phase transition ended. And a really nice model that does this is this like Ricci is coupling the morphon to a Ricci scalar. And so we have this non-minimal coupling. Like again, we're not the first people to study this non-minimally coupled scalar fields. And so this is the coupling to the Ricci scalar. And like you might think that naively, like for a constant equation of state, you have this expression for the Ricci scalar that is proportional to some prefactor times Hubble squared. And then in radiation domination, which is like true for the region we're studying, the equation of state is about 1/3. So you think, oh, the Ricci scalar vanishes, so this isn't going to be very helpful. But like, you know, immediately you can see that the Ricci scalar is proportional to the trace of the stress energy tensor, and so the trace anomaly will generate a non-zero Ricci scalar, right? So anything that breaks scale invariance, and like the first thing that runs into anyone's mind when you think about the trace anomaly is like the running of couplings, right? So clearly we have anomalous breaking of scale invariance like throughout the whole region we're interested in. And so like the Ricci scalar is not 0. And so we can get this like dependence of the dark matter mass on temperature. So I'm going to zoom in on the region we're interested in, which is like most of the dynamics for the way we set up this phase transition happen like between like 10 GeV and 0.1-ish GeV, and like right around confinement, basically. So in the region of interest, we have running couplings, we have QCD confinement, and we have mass thresholds. And those are the 3 sources of scale invariant breaking, breaking of scale invariance that could generate a non-zero Ricci scalar. And then like if that scale invariance changes with, and then like this, if this prefactor in front and it still scales like Hubble, then we get this nice like scanning behavior from the mass. And so like we can do a perturbative analysis and estimate the Ricci scalar's evolution based only on the perturbative running of couplings. And we did this just to sort of get like a feel for how this would evolve. And I've plotted this in the bottom left corner of this slide. And in the top right corner, I've shown the various sources of breaking scale invariance. And you can see that if I'm just looking at the running of the couplings, I'm not going to get a very good estimate of the mass threshold and how that like affects the evolution of the Ricci scalar, right? Because like, you know, the beta functions aren't super sensitive to that, just like small kinks. And I'm also gonna have a lot of problems when I try to like do any analysis at QCD confinement, because like the perturbative analysis breaks down there, and you can see that like reflected in this plot where I've plotted Hubble, and then the teal line is the square root of the Ricci scalar. And you can see it has this nice behavior where it's sort of like proportional to Hubble-ish. And then like at QCD confinement, the perturbative analysis breaks down. So like probably when you do something a bit more sophisticated, and luckily we don't need to because somebody else already did it. And so there's already been a full analysis of the Ricci scalar evolution, like for the standard model and for like a few other models done by Caldwell and Gubser in this paper here. And I just lifted this plot directly from them. And then we can turn this, like their calculation of the Ricci scalar, which you can see they've labeled their y-axis 2 different ways, but the one we're interested in is the one on the right, where it's like directly the Ricci scalar. And then we can turn that into like a dependence on temperature in the region we're interested in. And then just to sort of like give a little bit more intuition for what this is, they've shown like, so like you can see like the bottom frame of the plot on the left shows like the deviations of the Ricci scalar from Hubble. And so you can see like sources of scale invariance are gonna like show up as little bumps. So like the electroweak phase transition is there at like 10 to the minus 15th in the scale factor that they've plotted. And then like electrons decoupling from the thermal bath is here at like around 10 to the minus 9th A over A naught. And then QCD confinement is like this large bump here, like shown by the red star. And then like when you translate this into the Ricci scalar's evolution and temperature in the region we're interested in, the relevant piece of scale invariant breaking is QCD confinement, and that's showing up there on the plot here, which is like our translated version of the results from this paper. So hopefully this like makes it a little less like mysterious how we're getting this, how this scalar field coupled to the Ricci scalar and how its dynamics are changing with temperature. And so at high temperatures, if you like take this potential and you minimize it, you see that at high temperatures, the morphon develops a non-zero VEV that depends on the Ricci scalar. So this VEV is a function of temperature through like the Ricci scalar's dependence on temperature. And what you can see here, I've plotted on the right, now I'm no longer showing a sketch of the potential for the morphon field. I'm actually showing the potential for the morphon field and showing different values of the potential as the temperature changes. And then on the left, I'm showing the evolution of the dark matter mass, given that it couples to this morphon field, which has this temperature-dependent VEV through the morphon's non-minimal coupling, or the coupling to the Ricci scalar. And this nicely gives us the behavior we want. So for a few benchmarks, I've chosen a few final masses, like the blue, green, yellow, and orange lines are different like final dark matter masses, like the masses that they have when the phase transition ends. And you can see for all of them, they sort of scan, they like start with some very high mass, and then like the mass decreases, and then they scan through the value of half the Higgs mass, which would be the value where they have where the dark matter has resonantly enhanced interactions. And then it continues to decrease until it hits its final mass and then it exits this evolution. So this is how we like built a model to capture the behavior that we wanted. And so now the next step is, all right, we have our phase transition, we have our temperature dependent dark matter mass, we have how it interacts to the standard model through the Higgs portal. So now what we need to do is calculate like the Relic abundance, right? So the most general or the most like common and best way to do this is to use to solve the Boltzmann equation. And as you can see, like an input into this Boltzmann equation is the thermally averaged cross section. And this like seems simple, but this was numerically like the most challenging, I think, part of our paper. So the first thing is to just calculate the cross section, which is straightforward. You can use the narrow width approximation to calculate the annihilation cross section of dark matter near the resonance peak. And then we took this, using this result from the literature, you can just calculate the cross section of like this the dark matter to Higgs to standard model final states. And this is the same plot I showed you earlier. But we also need to thermally average this result, right? And we need to calculate, like, for our analysis, we need to calculate this a lot of times and thermally average. And so thermally averaging like poses two challenges. The first one is like purely practical. right? So we need to do a quick thermal averaging around the resonance peak. And we're probably not the first people to do this, but we had a lot of trouble doing this quickly. And so, you have this standard procedure that comes from like understanding the momentum distribution functions, and then like rewriting this as a function of the center of mass energy and temperature, or as a function of the center of mass energy, and then you integrate over it and you get a thermally averaged cross section. But this integral varies very, very rapidly around the resonance peak. And so like the strategy that a lot of people use is they change variables. So you can use this nice variable eta that I've defined here. And then you get the same integrand in different variables. And this integrand doesn't vary rapidly around the resonance peak, but it does vary rapidly everywhere else. And I showed like kind of if you just pick one temperature, you can plot like the cross section in S and in eta. And you see like, if you plot the cross section in S, you get this quick variation at the resonance peak, but in eta, you get quick variations on the edges. And so basically what we did is we split the integrand up into various regions. So like we use the variable, like when we like switched back and forth between the variables, and in a region where there wasn't quick rapid variation, we used quick sampling to do the integral, and then sort of like patched these regions together to get our answer for thermal averaging. And this way we were able to like thermally average, like to plot the thermally averaged cross section as a function of temperature, and like also thermally average for like many points that we examined. So this is how we solved the practical problem. And like it was quite nice what we ended up with. So the blue line is our approximate curve. So this is like what we got through our approximation method. And then the light blue points are like our brute force, just like numerical integration through the whole region in one variable answer. And you can see that like the approximation method we used, where we sort of switched variables and sampled, where in the variables that weren't varying rapidly, gives like very good matching with the full numerical integration answers, like even around right near the resonance peak, and like where the resonance peak is changing quickly, or where the cross section is changing quickly around the resonance peak. So we were pretty pleased with that. And so now I've like still only, so I think you've seen this plot before, but now I have enough information to tell you everything that's on the plot. So here, like we show how various things change with temperature, and for this benchmark, sorry, 1 second, I'm going to move the little video window so that it's not blocking too much of the slides for me. Okay. So basically, for this plot, we've chosen like a morphon mass that's 10 to the minus 10 EV, and like a final dark matter mass that's 1 GeV. And then we've plotted like the dark matter mass as it changes with temperature. And then we've also plotted our approximation of the thermally averaged cross section plus like the full numerical integration. And then the top two lines are Hubble as a function of temperature, and then the square root of the Ricci scalar. And all of these values are in GeV on the y-axis. And so, yeah, like you can see that we have exactly the behavior we want. The full numerical integration matches the approximation, and we get this nice peak right as the dark matter passes through the Higgs, half the Higgs mass. But there's another problem with thermal averaging. So like that was the practical issue. But there's also the issue of like is thermal averaging like are we doing this correctly in the situation where our dark matter mass is temperature dependent? And so like, do we know that we understand the momentum distribution functions throughout the entirety of the phase transition? And so like this like equation where I've written the thermal averaging prescription in terms of S originally, right, comes from momentum distributions of the various particles involved in the interaction. And so like if like the dark matter is changing, like are we sure, or the dark matter mass is changing, are we sure this isn't having an impact on the momentum distribution functions? And if it does, like are we even allowed to use this thermal averaging expression, right? And so to answer this question, we kind of came up with 3 conditions that we think are like reasonable and maybe a bit conservative to say that like in this region we can trust that we can thermal average. And so the first one is like not something we came up with, but like that anyone needs, is that we require that we're in kinetic equilibrium in order to like use these distribution functions and thermally average. And that's that the scattering rate is bigger than Hubble. So we need to make sure that we're in kinetic equilibrium. in the region where we're using this thermal averaging. And then another thing that another condition that we imposed is that the reactions that establish kinetic equilibrium, meaning the scattering rate, are faster than the mass change. So we required that the scattering rate is bigger than m dot over m. And then, so we think if these two conditions hold, then then at least we can trust that like our momentum distribution functions are appropriate and like our computational method reflects the physics. And then finally, we wanted to avoid non-perturbative particle production, so we employed the adiabatic condition, which is a condition on how quickly the mass of the dark matter is changing. And so given these three conditions, now we think we understand theoretically that it's appropriate to thermally average, as well as understanding like the practicalities of doing it. And so now, the next step after given like this, the last slides I said sound boring, but they were like the most computationally difficult. And this is like where the interesting physics happens, but it computationally wasn't so hard. But we have to solve the Boltzmann equations with dark matter mass that's changing, which we thought would be challenging, but in the end wasn't so hard. So, you know, you can rewrite the Boltzmann equation. Once you have the thermally averaged cross-section, you can rewrite it in terms of temperature, assuming radiation domination. And then like Mathematica has like built-in differential equation solvers that do a very good job solving this for our model. And then the only real trick we used is that we had to, when there were problems, we broke this up into small steps. And then we also like switched dynamically between like solving the log form or the exponential form of this equation, and then like patching the solutions together at the boundaries. And this like worked pretty quickly and wasn't so difficult. But so yeah, that's the next part of the analysis that we did. And here's an example of a result for a benchmark. And let's pick like a very light dark matter benchmark, so a final mass of 10 MeV. So I showed a version of the plot I showed you before, but for a different benchmark. And so this is the same thing with different parameters on the right. And then on the left, I show you the evolution of the yield. And so there's two like very important qualitative features of the figure on the right. Sorry, of the figure on the right. So the figure on the right, like now temperature, like, so as temperature decreases, time moves forward. So now time is moving from the right to the left on this plot. And basically like the first important feature is the one we expected, right? Is that the yield is going to see this bump and this like significant increase right around the resonance peak. And like in the dark matter's history, that does occur. And you can see this happening, like we've highlighted the resonance peak with this vertical dotted line. And then the end of the phase transition is the vertical teal line. And you can see that like in the dark matter's history, like there is this increase in yield right around where the dark matter has like resonantly enhanced interactions with the standard model. But the more important feature in this figure is one we weren't expecting, which is that in fact the yield like continues to increase very significantly and during the phase transition. And this just has to do, so like if you look at the plot now on the left, you can see that like there's this big bump on the resonance, but there's also this shoulder, right? And for this specific benchmark, the shoulder is pretty pronounced. And this shoulder is like shows you the rate, and it like reflects the fact that like as the mass is changing, the equilibrium number density of the dark matter is changing. And the equilibrium number density, if you remember on this slide, it feeds into the Boltzmann equation. So it has the effect of sort of dragging the number density of the dark matter up. Even like when you're no longer having resonantly enhanced interactions, it's still dragging it up. And so this like increasing equilibrium, which is like not a typical type of thing that you wouldn't have seen this without the temperature dependent mass, actually has this huge effect of like dragging the yield up, which is like an interesting result that we didn't expect. And so on this benchmark, you can qualitatively see both, but actually in this plot I'm showing you, the equilibrium increasing is like the more important effect. And yeah, and so also another thing to say about this plot is that this is similar to Friesen in that this dark matter never enters equilibrium. So this is not a thermal production, but it's always out of equilibrium, and it's just being produced through weak interactions with the standard model, like at some point very strong, but then weak again until its Relic abundance is set at the end of the phase transition. And so that was just one benchmark. And what we can do is we actually made a plot of like many benchmarks. So like we extended this into many final dark matter masses. And you can see how like now this is very similar to a plot I've shown you before, but it extends into much lighter regions. So now the dark blue solid curve is the relic abundance for like the standard WIMP Higgs portal dark matter. And then the orange and the light blue curves are the results that we get as the relic abundance line. So what couplings we need for which final masses to reproduce the relic abundance. And we've chosen two values of morphon mass, so like two benchmarks for the phase transition. And one is a morphon mass that's like 10 to the minus 9th eV, and one is 2 times 10 to the minus 9th eV. So like double the morphon mass. And you can see this nice effect where because of these two properties, one, the resonant enhancement, and two, this like changing equilibrium number density due to like the phase transition itself, we can actually reproduce the relic abundance for much, much smaller couplings far below like direct detection limits and Higgs to invisible decay limits. And then we've shown on this plot two shaded regions. And these are regions that we say are ruled out, in that like if our relic abundance line enters this region, which it does for the blue relic abundance curve, it's not necessarily that this is ruled out, but it's that we don't trust our computation in this region. And so these are like regions where we violated the thermal averaging conditions we put forward before. So first of all, the adiabatic condition, the condition that we don't have any non-perturbative production of dark matter, that condition like is applied to the whole region. So we haven't shown, there's no like curve on this graph. It's just true, the whole region satisfies the adiabatic condition. But the fact that we have the scattering rate bigger than Hubble, and also that the scattering rate needs to be faster than like the mass change, we've shown that on two shaded regions, each corresponding to the curve that shares its color. And then the like kinetic equilibrium is a bit more imposing than the second constraint that the interactions that establish kinetic equilibrium need to be fast. But we've shown those both on the plot, so you can sort of see qualitatively what's going on. And for the orange line, we never run into that problem, but for the blue line, we do run into that problem. So there's some region where we don't really trust our calculation. And that's not to say that the calculation can't be done if someone finds it interesting. It's just like harder and would require like a better understanding of the momentum distribution functions of the particles as the dark matter mass is changing. And so like maybe it's interesting to see a few more benchmarks, right? So I already showed you the 10 MeV benchmark in a previous slide, but I'll just like quickly show it again just to say that the relic abundance here is mostly controlled by the behavior of the equilibrium number density of the dark matter as its mass changes. And then like, let's see what happens as we go to heavier dark matter masses, right? So here's an example for 1 GeV where the shoulder isn't quite as pronounced, but you can see there's still like a pretty important shoulder on this curve that shows the cross section, that the annihilation rate as a function of temperature. And you can see here, again, like because the mass is larger, again, on this curve, you can see that the equilibrium number density of dark matter is the more important feature than the resonance, though it still does have this history of the resonant enhancement. And perhaps a more interesting benchmark is 10 GeV. And here, where the final mass of the dark matter is 10 GeV, here the relic abundance is entirely set by the resonant enhancement. So now the resonant enhancement is the most important effect in the dark matter's history. And this like increasing N equilibrium is like not so important because like, you know, all you have to do is assume that the number density is low as an initial condition for freezing. And you still end up with the same yield in the end. So like the resonance peak is going to bump you up depending on your initial conditions. So this like initial increase isn't so important. And you can also see that reflected on the plot on the left, in that the shoulder of this like curve of the annihilation rate is just not as pronounced. And then finally, one thing I didn't say about, so let me go back really quickly. One thing I didn't say about this is that we want to know like whether the dark matter has a history of being thermalized. So was the dark matter ever in equilibrium for any of these points? And for the blue line, that was never the case. We could only find benchmarks where it was produced out of equilibrium. And for the orange line, we did find benchmarks where the dark matter entered equilibrium right on the resonance, but those were all ruled out. But I'm still, so you can see that like the dotted vertical orange line shows this region like that, the dotted orange line and to the right shows this region. And you can see it's all ruled out by xenon 110. But I'm still going to show you a benchmark from that region, just so you can see like what happens. So here's like a final dark matter mass of 40 GeV. So you can see the phase transition like didn't really morph the dark matter very much from its 1/2 mH value that like had the resonant enhancement. And here again, like the resonance has a huge effect on the evolution of the yield, and because it's thermalized, it's entered thermal equilibrium. Like it's completely insensitive to initial conditions, and this is like a thermal dark matter production mechanism. Unfortunately ruled out. It would have been nice if we had like a new thermal production mechanism in like not ruled out parameter space, but here's an example of what it would look like if it weren't ruled out. And here you can see like it is precisely the resonance that's responsible for allowing the interaction, the cross section to be large enough that the dark matter is briefly in equilibrium in the standard model. Okay, and so now one more thing I would say is that I said there are these two qualitatively important effects. And in fact, like you can see on the orange curve, this like wiggle around 10 GeV. And this wiggle, I think, comes from like crossing over from the resonance being the most important effect to the like increasing N equilibrium being the most important effect. So you can see there's kind of like qualitatively different evolution of the Relic abundance based on these like based on which of these two effects is most important. So like for a lot of our parameter space, it was the effect that we didn't expect. So in summary, we provided like a pretty detailed study of the evolution of dark matter with a changing mass, and like doing this really like carefully actually like showed us something we didn't expect. And we defined 3 conditions to check the validity of thermal averaging if you have dark matter that's undergoing a phase transition, which I think is like a nice result. And then we also provided a concrete model that like allowed the dark matter evolution to scan from heavy to light and to like generically pass through a history of resonant enhancement. And so we have this like sort of freeze-in like new mechanism for producing light dark matter through the Higgs portal, like freeze-in with like a few like qualitative caveats, like different caveats. And then we have like this in our mechanism, the dark matter always scans through the Higgs resonance peak. And we found that we get much smaller portal couplings than standard freeze out due to both the history of resonant enhancement, and then also the behavior of the equilibrium number density of the dark matter during the phase transition. Thank you.
Awesome. Thank you, Rachel. I really enjoyed the talk. So I actually have a few questions myself, but I'm going to first ask if anyone listening has a question first. So I'll wait a few seconds. Okay, I guess I'll go first. So you, at the end, you showed a lot of these figures talking about the phase space. It's been ruled out by like the xenon experiment with the phase space of the mass and of the coupling strength. Because this model also needs this morphon field, are there any experiments that could try to probe that that object, or is it entirely based on this dark matter mass phase space?
Yeah, so the morphon does have some bounds. Specifically, it's super light, so there might be fifth force constraints, right? And that's why but the morphon, so I actually have a backup slide on this. Okay, so the morphon is a pseudoscalar, which we chose like for the reason to avoid fifth force constraints, and because like it's so light, maybe like it could be a pseudo Boltzmann boson or something, but we didn't like provide a UV complete model. But yeah, so because it's a pseudoscalar, like the fifth force constraints are like this diagram is forbidden, right? And so basically the pseudoscalar, the morphon only talks to the dark matter. The dark matter only talks to the standard model through the Higgs, right? So like no matter what you do, even if it's not this one loop diagram, if you have like some other like blob in the middle, you always have this, you're always like have to deal with this mixing if it's like one morphon production. You could worry about like 2 morphon production, like cosmologically. In experiments, I'm not sure how you'd see this. It would be like really, really invisible, right? Maybe the Higgs to invisible decay, like I mean, this is a really, really light particle that only talks to the Higgs through like dark matter, which also only talks to the Higgs. But like, yeah, cosmologically you could worry about it, but like based on like our early decoupling temperature, this like really light field like actually gets diluted just from the entropy evolution. So yeah, those are the only 2 probes that I know of the morphons. I think it would be really hard to see.
does this I also have a question about the morphon? I mean, does it have an origin, or is it a new proposal that you make for a new field? And does it belong in the dark sector or somewhere else?
Yeah, I mean, it would be in the dark sector, but it wouldn't be a very large amount. Like it would just be produced, like even if it's produced just at its equilibrium number density, it wouldn't make up a huge amount, just like this production is really small. And so, sorry, what was the start? So you were asking, does it live in the dark sector? It does, but it can't explain dark matter. It's very, very light and there's not very much of it. And your other question, sorry?
Can you motivate this presence from somewhere else, or is just a brand new?
Yeah, so I think something that would be interesting would be to see if it's like a pseudo Goldstone boson, right? Because it has to have like a pretty flat potential, and it has to be really, really light, and it's a pseudoscalar. So like maybe some like non-minimally coupled like axion-like field or something, but we didn't actually provide a UV complete model. We just like said it had the properties that it needed to have to like give us the phase transition we wanted. But yeah, I mean, that is an interesting direction to like see what the origin of this field is and like what the UV complete explanation for it is.
Thank you.
Mm-hmm. And then like maybe to expand on that, like this isn't the only phase transition that can give you what you want. Another one that would be like way simpler is just a rolling scalar, but we kept running into problems where our rolling scalar kept oscillating back up through the resonance. So in the end, it was just too hard numerically for us to find like a rolling scalar that had the properties we wanted without having this like really complicated oscillation behavior, which we didn't want. And so the Ricci scalar had this like really nice, just simple scanning behavior. So we found it preferable as like just like as an example to use to show this mechanism, though I think you could like accomplish the same thing maybe with some other kind of phase transition.
Great. Okay. Thank you.
Mm-hmm.
Okay, so I have another less scientific question, just because I'm always curious about anything that has computational aspects. So how much were you limited by the complexity of, I mean, you said for the easier part for the PD, you used Mathematica, but like when you were trying to do the calculation of the Ricci, well, the thing with the integral where you had the singularity that needed a different variable.
Yeah, just literally just thermally averaging the cross section.
Right.
I mean, it's not interesting. I mean, it's a necessary physics calculation, but it's not very interesting, right? Yeah, it was really hard. I mean, in the end, like we worked really hard at it, and in the end, like Juna had found the fastest way to do it, and we managed to get it down to like you know, like being able to like really quickly generate enough points to interpolate nicely, like maybe like, let's see, I'm trying to remember for myself, maybe like between 5 and 10 seconds for each time we ran this for one benchmark, for example. So yeah, I thought that was really fast because the first time I did it, it took like, you know, like so much time I had to wait.
Yeah. Well, because you're scanning so many different variables, you have to do it over and over again to make the plots for the final thing. Yeah. Exactly,
because it's not like, you know, if you choose a coupling, right? It's not like that coupling is going to necessarily give you the right relic abundance, though we did find like a quick relationship. So once you had one and then you got the wrong relic abundance, you could quickly correct to the right one. Just from like trial and error, we could really quickly see that those things scaled. So in the end, we were able to like cut our computation time a lot, but really the limiting factor was still, even with like our like fancy like sampling quick approximation method, that was still like the slowest part of it was much slower than solving the Boltzmann equations, actually.
Right.
Yeah.
Okay, thank you. Yeah.
Mm-hmm.
Okay.
Yeah, if I may go back to the morphon one more time, if you please allow me.
Sure.
What was the reason you chose it to be a scalar?
Well, we chose it to be a pseudoscalar.
Yeah, but I mean, not a vector or pseudo vector or a pseudo tensor.
Oh, I guess I didn't even think about using a vector. I don't know.
Because I'm asking because lately there is this trend. There are a couple of papers by Riotto or other people that use some higher rank tensors living in the dark sector. They're massive, motivated from string theory, I guess, because the spectrum of string theory has all these massive higher spin modes. So I was wondering if one could, if there is a reason why you chose it to be a scalar or pseudoscalar instead of a pseudo tensor.
Yeah, I mean, probably just minimalism. I guess I don't know. I'd be interested, but I don't know the advantages to going to these like pseudo tensor states, like off the top of my head. And like for me, the first thing I would think, if we want to couple something to a field that attains a Z and contributes to something's mass, I would think a scalar field. And then we found out it had to be a scalar field with a really flat potential, and we had this fifth force problem, so a pseudo-scalar field made sense. And I think that's as much as I considered going to like.
Right.
Or
because if you consider, for example, to be higher rank tensor, you will need a higher derivative terms to couple it, and this will be another way to do the non-minimal coupling you were doing.
Oh, interesting. Yeah. I mean, maybe that's interesting application. Yeah, it might change the shape of the evolution with temperature, right?
Okay, so if there aren't any more questions, I'm going to say thank you one more time for Rachel, and then stop the recording. And if anyone has any kind of casual conversation to bring up, we can do that after the recording stops. Thanks, Rachel.
Thank you.